Good evening, everyone. My name is Sir Jude, and here's the video lecture of our lesson that we tackled this morning. So, yesterday, our entire lesson was about the converging or concave mirrors, and we spent too much time with the ray diagram that we no longer had time to explain why concave mirrors are called converging and the practical applications of concave mirrors. So, we kick we kick-started our lesson earlier with answering this question. So why are concave mirrors called converging? So first, in terms of curvature, they have an inward curvature, no? And this shape or form or appearance rather explains or is responsible for the second reason. Why? So you have a smiley here as our object, which is placed very far from the mirror. So in this case, it's infinity. And you have four solid lines here that are represented in different colors. No, so they represent actual light rays. And then once they hit the edge of the concave mirror, they start colliding or converging towards the focus. So aside from the inward curvature, concave mirrors are called converging because when an object is at infinity, no, way beyond C or way beyond the reaches of curvature, the actual rays converge at the focus, or in this case, it's letter F. Now, speaking of practical applications of concave mirrors, what are converging or concave mirrors for? So here, I combined all the three cases from object beyond C to object at C and object between F and C. And what's common among these three cases is that all of them have inverted images. You might be wondering, no, is there really, aside from fun or optical entertainment, is there really any essence for inverted images? So I look for different, I research for different, for various tools or gadgets that can be relatable, especially to you, my students. And the only thing that I can find is that is also easy to explain is the dental mirror. It's because when you're in the point of view of a dentist who can only see the front teeth, no, you can use the concave mirror to access the back portion of the teeth as well as the upper back portion wherein there can be tinga or stock food or tartar or plaque or whatever else. So you don't need to lean over or to lean closer to the patient just to see the back portion or the upper back portion of their teeth. Now, next, for case number four, wherein there's no object because the lines, whether it's solid or broken, never intersected. No, the two most relatable or basic applications are these a flashlight, and in this case, we have the headlights and the taillights for vehicles or transportation, specifically in cars. No, so this is just really a parallel light beam, no, because there's no image form even though the image is literally at infinity, no, we can only have parallel light rays, no, that can help us navigate through certain areas, especially when it's dark in the case of flashlight, or yeah, especially in the evening wherein there's limited visibility because there's no sun, no, and there's only the moon, and cars might be colliding with each other if not for the headlights or the taillights. And for case number five, no, the two most practical applications that I can access was the makeup mirrors and the shaving mirrors. So notice that for my examples, no, they still use plain mirrors, but I think concave mirrors will be applicable for this one because normally when one applies makeup or when one shaves his mustache or his or her mustache or beard or other facial hair, no, you move closer to the mirror because it will give you case number five, in which the object becomes magnified. So you can spot which areas need some lightening up or darkening, or which areas of your face has a poorly unshaven portion. Okay, so at this point, we're now finally closing our chapter on converging or concave mirrors, and we will move on to diverging or convex mirrors. So the difference between the ray diagram of diverging and concave mirrors is that in this case, the ray diagram is somewhat expanded in a way that we have duplicated focus and the radius of curvature because for concave mirrors, they're only focused mostly on the left side, say for case number 5. All right. So I also ask you to tabulate or to craft the table for the loss interpretations of images formed by diverging or convex mirrors. So on our first sample problem, we have a 9 centimeter tall Markey number, which is 14 centimeters in front of a convex mirror with the focus of 6 centimeters. Rate the image and interpret its loss. So the best thing to do before you start the ray diagramming is to determine the focal length and the radius of curvature. So in the problem, the focus is already 6 centimeters. And with that, the radius of curvature will be 6 times 2, which is 12 centimeters. Okay, so those are the numbers written on the left side or in front of the convex mirror. And because you have duplicated focus and radius of curvature, an extra pair on the other side of the mirror, then they still have the same magnitude but with different sign this time. So the focus on the right side will be negative 6 centimeters, and the radius of curvature on the right side will be negative 12 centimeters this time. So all problems, no, or all problems, all ray diagrams for this topic will be using these four values. So now let's focus on the underlying number. So the Markey number is 14 centimeters in front of a convex mirror. 14 centimeters greater than 12. So that means that our first object number 1 is beyond C. So because we're tackling a different mirror this time, no, we will have a different ray diagram. No? So as you notice, we have different ray diagram for plane mirror, then for concave mirror, and now for the convex mirror. So how does the ray diagram look like? Like that. I will not explain now because we literally had this morning, and it's going to be very repetitive. Our focus of the video lecture is just for the review, especially for those who were absent. And this time, the intersection happens between two broken lines. So therefore, the image, uh, that one. So object number 1 is literally flipped. Its left and right sides are reversed this time around. Okay, so we will not interpret loss in this case as of the moment. I'd like to say that for the last because there's a reason why. So in the meantime, let's now move on to the next problem. So this time, a Markey number is 12 centimeters in front of a convex mirror. 12 is actually the radius of curvature in this example. So we put object number 2 at C. And by performing the ray diagram, no, you have two broken lines or imaginary light rays intersecting again at the right side. So because the intersection happens at the top of the optical axis, then therefore the object will be laterally still upright, but laterally reversed or inverted. Okay. Next, we have case number 3, wherein the Markey number is 9 centimeters in front of a convex mirror. So 9 centimeters is found between 6 and 12. That means our third object, number 3, is found between the focus and the radius of curvature. And by performing ray diagram, no, once again, for the third time, you have a pair of broken lines intersecting at the right side, and point of intersection happens to be at the top of the optical axis. So therefore, number 3 will be upright but laterally reversed. Next, number 4. For this case, no, the Markey number is 6 centimeters in front of a convex mirror. So our object will be at the focus. So remember that way back in case number of concave mirrors, no, we don't have an actual object, or rather the object, we have an actual object, but the image is considered at infinity because the solid and the broken lines never intersected. They are parallel with each other. So will that be the same case for case number 4 of convex mirror? Let's find out. So by performing the ray diagram this time around, it will not be the same as case number 4 for concave mirror because there is a point of intersection between broken lines found at the right side of the mirror at the top of the optical axis. So in this case, we have an image which is a upright and laterally reversed version of our object. And now, lastly, for our final case, we have the marquee number 3 centimeters in front of a convex mirror. So 3 is found between, sorry, 3 centimeters, or in this case, our object is found between the mirror and the focus. Because remember, V, or the vertex, is always 0 because that's where the mirror is located. That's our point of reference. So from our by performing the ray diagram, once again, for the fifth and final time, no? Point of intersection by two imaginary light rays or two broken lines on the right side of the mirror at the top of the optical axis. So therefore, you have an upright and laterally reversed version of number 5. So notice that compared yesterday, wherein we have loss for each case, I decided to interpret the loss this time after case number 5 because all images formed by convex mirrors have only one loss interpretation. So in this case, no, all images are always found at the back of the mirror, specifically between the vertex and the back focus. The next, the orientation of all the images is always upright and laterally inverted. We're in same orientation as the object, but reversed left and right sides. Left becomes the right, right becomes the left. The size, all of them will be reduced, no? So the height decreased compared to the height of the object. And finally, because the intersection happened between two broken lines or imaginary rays, then therefore all images will be considered virtual. And that's it for the ray diagram of images formed by convex mirrors. This is compared to previous lesson. This one is relatively easy but somewhat boring because there are no surprises or no deviations from the trend. No, I'm not saying it's bad because this one is technically more manageable, faster to be accomplished compared to the ones we had yesterday. Yesterday was more challenging, kind of trickier, but at the same time more fun because in each location wherein you put the object in front of the concave mirror, you have a different loss and different appearance of the image. But with practice, no, then you'll be able to overcome these setbacks and difficulties. So now let me just recap the loss interpretation for images formed by diverging convex mirrors, regardless whether you put it anywhere, no? Cases 1 to 5. All images will be found at the back. They will be upright and laterally inverted, always reduced, and formed virtually. Now, we started this video lecture with answering the question, why are concave mirrors called converging? So we will end our discussion with this question, why are convex mirrors called diverging? So remember when we were discussing divergent boundaries way back in first quarter, when we say divergent boundary, the two crusts are separating from each other because of tension. So in this case, we have still two reasons why. So first, it is the divergence is responsible is caused or is an offshoot by the outward curvature of these mirrors. And the second reason, no, using another smiley face which is way beyond C, no? Smiley face is at infinity, no? So you have these four solid lines representing actual light rays. And once they finally hit or strike the edge of the convex mirror, each of them start to deviate, no, or diverge. However, no, in ray diagramming, we have a continuation on the right side because once you extend these light rays using broken lines, not or they represent imaginary light rays now, they now converge at the back focus. So this one is trickier to answer compared to our initial question in this video lecture because when an object is at infinity, no, the actual light the actual rays diverge. But the imaginary rays, when you extend, the actual light rays at the back of the mirror, they converge at back focus. Now, finally, for the practical applications, this one is relatively easy. The same level of what do you call this? Same level of easiness compared to plane mirrors because of all the three types of mirrors, it's the plane and diverging mirrors that are always uh available and dare I say more useful for us human beings. So what are diverging or convex mirrors for? So let's start with the basic one, which is the one at the left. You see these types of mirrors in convenience stores like 7-Eleven or Mini Stop or other grocery or department stores, or even in parking lots. So the reason why we use them is because if you're a security guard, and since technically you're expected to be at your station wherein you're supposed to safeguard no the entire establishment to prevent suspecting people from entering or kidnapping or whatever crime committing inside an establishment, no? With convex mirrors, if you're a security guard, and let's say, for example, there is a shoplifter in a grocery store, not only that you have a wide or a comprehensive view of the surroundings, but you will also can pinpoint or can witness if there's a potential shoplifting happening, no? Because some customers might be stealing or hiding some stuff that they will not likely pay. But of course, CCTV is much more effective in that case because there's a virtual evidence. Because if you're an passerby or an onlooker or just a visual witness, then therefore your testimony might be uh what do you call this? Might be declared as hearsay. But still, again, let's not be too overly critical and technical with this one. This is where diverging and convex mirrors will be useful, no, for security purposes. Now, on the right side, no, I know that the rear view mirror and the side mirror in cars that I featured here, all of them are plain because they are flat. But there are some cars wherein, there's curved outward curvature. That's why this is also where diverging or convex mirrors can be useful, no? Because I don't think concave mirrors will be beneficial or advantageous for the driver because especially if the cars behind you, if they're too far, they will just give you an inverted image because that will be weird and confusing, especially if you're the one driving, no? But we're using convex mirrors is because not only again it will give you the comprehensive view at the back of all your surroundings at the back since as a driver you're supposed to be paying attention to the one in front of you, no? But you will also have all objects behind you, no, that are approaching you from behind will be reduced, no? One of the characteristics in the interpretation laws is that all images will be reduced. And in case you have a passenger that's like super afraid of heavy cars, no? Then therefore there's no reason to be panic or to have anxiety because all images will be reduced in that case. So I think uh that's the end of our discussion about mirrors, both plane and curved, no? So I using ray diagrams, I explained and connected the ray diagrams of each plane mirror to the respective practical applications. So good luck for your upcoming performance task tomorrow, and you may want to research some more practices and practice more about the ray diagramming. So in order to get cleaner and let's say sharper drawing or sketching of the images and the arrows. Okay, see you tomorrow and good night.